Number 2, it says use partial fractions to show the series is convergent. So do you remember how to find partial fractions? You have 1 plus 0x over n times n plus 1. Does that sound familiar? It would be 1 plus 0x or 0n. I mean, it's just going to be 0. I want to say it's n, but I'm not sure. But anyway, this is going to be equal to a over one of these factors, n, plus b over n plus 1. Have you done that before, Aiden? Oh, good. You've done that.
Where is the 1 plus 0x
I'm pretty sure this is right. So what we're doing is we're going to get common denominators here, and you're going to get 1 plus 0 times a variable, n times n plus 1, equals a times n plus 1 plus b times n over the common denominator n times n plus 1. So I got a common denominator of n plus 1, n plus 1, n. Does that look okay? Can we ignore this denominator now because these are the same denominators? Are you okay with me doing that? I'm just going to erase that and that. All right. So when I have 1 plus 0 times x, I'm going to get a n plus b n plus a. I think it should be n. So you're going to have 1 plus 0. Yeah, it should be n. Little things like that bug me a lot. Is equal to a plus b times n plus a. Okay, so what does the 1 map to? A. What does the 0 map to now that the n's are correlated? A plus b. So from partial fractions, you can say a plus b is equal to the coefficient of n, which is 0, and a is equal to, oh, I like this, 1. So what's b going to be? Negative 1. So the partial fraction that we're going to have is going to be the sum n equal 1 to infinity of a, which is 1 over n, minus b is 1 over n plus 1. We changed this a here to 1 and b to negative 1. And with that, can you see how that turns into 1 over n and negative 1 over n plus 1? So now we're going to take this series and find out whether it converges or not. So this is going to be 1 over 1 minus 1 over 1 plus 1. Then 1 becomes a 2, plus 1 over 2 minus 1 over 2 plus 1, which is 3. Then 2 becomes a 3, 1 over 3 minus 1 over 4, all the way to 1 over n minus 1 over n minus 1. N plus 1, thank you. Now everything is going to cancel out except for a what? 1 minus 1 over n plus 1. But if we're looking at adding this up as n goes to infinity, what does this approach? Just 1, because this goes to 0, right? So there you go, there's your 1. therefore converges at 1. There, we did all that. We got that part I. What do you think? 1 down, 10 to go. Hence, by using the limit comparison test, determine whether the series is convergent or divergent. What they're looking at there is saying that the sum is n equals 1 to infinity of 1 over e to the n times n squared. We're trying to see if that's convergent or not, right? And if we're doing the comparison test, I think what they did, a ratio test for this one. I think when I looked at limit comparison, I wouldn't do it this way. They did the ratio test. What's that? Oh, okay. So if we take the limit as n approaches infinity, they set a comparison test. If you want to, you can say that 1 over e to the n squared is always going to be less than 1 over n squared. And using, you remember the p-test? The power of n? 1 over n squared will converge. Therefore, since 1 over e squared n squared is less than 1 over n squared, and n squared converges, a little leftover there, and 1 over n squared converges. So I'm going to say that again. The p-test is the power of n. 1 over n diverged, but when you went anything bigger than a power of 1, as soon as that p was greater than 1, then it's going to converge. And so therefore, 1 over n squared converges, then 1 over, or e to the negative n over n squared converges by what? Comparison test. Because this one is bigger, and if the big one converges, then the little one has to converge too. Icky. Easier. For part B, it says show that the improper integral is convergent. So what they're saying is if you integrate from 0 to infinity of 1 over x squared plus 1 dx, that you actually get an amount. Okay, convergent means there's 3 things that you had to have. Do you remember this? One is all terms what? Wow, I'm impressed. That's been a long time. And also, we are something on interval. Decreasing terms on the interval, and what else on the interval? 3 things you have to write. Continuous. Impressive. Did you guys have to do this for integral test? Oh, I know, we'll get to that. But yeah, just the integral test, you have to have these 3, and each of these will be worth a mark. All terms positive, decreasing on the interval, continuous on the interval. For the ratio test, all you need is this top one. Now if we take this integral and we get an answer, it's continuous. Or, excuse me, it's convergent. This has an integral. Do you know what it is? 1 over x squared plus 1. Wow, they're amazing. Arctangent of x going from 0 to infinity is the arctangent of infinity minus arctangent of 0. Now, the way you would do this is you would write you would write the limit as n approaches infinity of the arc tangent of n. That's how you would show this. Minus 0. And as n goes to infinity, we're just doing this in Honors Pre-Calc right now. What does this go to as you go to infinity? Very good. And negative infinity goes to negative pi over 2. So this answer is positive pi over 2. Therefore, since criteria, all three, 1, 2, and 3 from above here, I'm not writing it again, and the integral from 0 to infinity of u of n dn is equal to a constant, which in this case is pi over 2. It's a constant. Therefore, series converges by integral test. Quick comment came up, and it's a good one. How could you prove decreasing? Let me show you that real quick. If you go u of n plus 1 minus u of n has to be less than 0. So for this one, it would be 1 over x plus 1 squared plus 1 minus 1 over x squared plus 1 is always less than 0. You could actually algebraically prove that. I wouldn't want to, but you could. And now we get to Aiden's comment about the alternating series. Do we like alternating series? We love them. We love them. Yes? Yep, it's these three criteria. They're really looking for those. In part C, it says show that the series is convergent. So what you need to do there is you need to show that as you go along here, those terms are going to be see how they're decreasing terms? Yeah, they have to be alternating, which they will be. And you have to, I think it's the decreasing A of n terms. I think you have to show that. And we kind of showed that before, or we indicated it before. Now all you have to do is take the limit as n approaches infinity of 1 over n squared plus 1 is equal to 0. Therefore, alternating series converges. You can fill that with more details. Converges, if you wish. If you wanted. If you wanted to list them, put a 0 here. You're going to get 1 over 1 minus 1 over 2 plus 1 over 5 minus 1 over 10, I think. And you can see that those are getting smaller, and you can see that they're alternating. Then all you have to do is make these two statements and then take the limit. If the sum of the above series is S, show that S is somewhere between 3/5 and 2/3. This one I think I can remember. If you took this sum as n goes from 0 to infinity of negative 1 to n of n squared plus 1, and you wrote them out, 1 minus a half plus, I think it's a fifth, 2 squared plus 1, 3 squared plus 1 is 10, 4 squared plus 1 is 1/17, like that. And if you were to add these three together, you're going to get 5/10 plus 1/10 is 6/10. I think this is right. 10/10 minus 5/10 plus 2/10. Isn't that right? Oh, is it 7/10? Right. Oh yeah, I'm going to do the next one. All three of these to get 6/10. All right. So there's your 6/10. There's your 3/5. Okay. Now, the alternating sum, the error, is less than the next term, a of n plus 1. What is your next term? 1/17. So take your calculators. What's 3/5 plus 1/17? I need a decimal for that. What's that? Thank you. That's right, too. I remember doing this one. It says if the sum of series show that S is between 3/5, well, we know it's between 3/5 and the next term, which is 1/17. S is somewhere between 3/5 and 0.6588, which is also less than what? 0.6 repeating, or 2/3. So that's kind of lame, but that works. It does it. That one's a little tough. Oh, we're doing great. So last couple here. For the series, x to the, is that x to the n? Okay. Determine the radius of convergence. So we go all terms positive for ratio test. And we could prove that by going u of n plus 1 minus u of n is going to be greater than 0. You could do that if you wanted to. But to do the radius of convergence, you're going to take the limit as n approaches infinity, and you're going to go x to the n plus 1 over n squared plus 1. And then what's the n, yeah, that's right. N plus 1 squared plus 1, right, over x to the n over n squared plus 1. Do you remember doing that? And then what you'll do, I'll let you finish this one, then you're going to find that radius of convergence, which will be 1, and then check the endpoints. Remember when we did this? Then we check the endpoints. We can do that tomorrow.